It's a great pleasure for me to introduce our speaker today, Dr. Ajit Datar, who is an eminent personality in chemical industry and academics. He's going to speak to us today about the heart and soul of most pharmaceuticals, that is GCMS and LCMS. Dr. Datar finished his MSc and PhD from Mumbai University in 1976. He is currently working as an adjunct professor in Khalsa College and a visiting faculty at several other colleges in Mumbai. To his credit, he has several publications and is a guide for PhD in Mumbai University. Dr. Datar was working as the ex-advisor to Shimadzu Analytical India Private Limited Mumbai in the Customer Support Center. Prior to Shimadzu, he was with Thermoelectron and served this organization as General Manager Advanced Mass Spectrometry. He served for Chromeline and RI Technology as Technical Director and Senior Manager respectively for 15 years. He also served ACC for 12 years. Apart from all of this, Dr. Datar has developed methods for characterization of catalysts and processed products using catalysts. He indigenously developed BET surface area analyzer and particle size analyzer. As we see, our speaker has immense knowledge and experience in mass spectrometry. I'm sure you are eager to listen to him and be enlightened by his knowledge. I now invite Dr. Ajit Datar to deliver his lecture. Thank you.
Yeah. Hello. Good morning, all of you. I hope my voice is coming to all of you.
Yes, sir.
Yes, sir.
Yeah. Okay. So, yeah, good. So, today I've chosen a topic which is related to mass spectrometry, but not directly a mass spectrometry, but GC and LC attached to it. Okay. So it is GCMS and LCMS. The theme of this particular workshop is know your molecule. Okay, so on the basis of that, the previous speaker, Dr. Sujata, had talked about the single crystal XRD and powder XRD, how it is useful for finding out the structure of a crystal and in general, even the structure of a molecule if it is converted into crystal. Okay, so the mass spectrometry is definitely little different than that. We do not require a crystal. Okay, we require a solution in which we can measure the molecular weight and the structure of a molecule. Okay, so it is the new title, which is KYM, that is know your molecule. It is equivalent to KYC. Okay, so which is with we are all familiar with. So it can be also converted as know your chemical as KYC, but then molecule is a better name for this because this molecule is very important. We have to find out the molecular weight and molecular structure, and for that mass spectrometry is a very important topic. So MS for MS, molecular structure by mass spectrometry. So that is what is the title for today's talk, and I will definitely try to share my presentation very quickly. Okay, so let me share my presentation very quickly, and then probably share. Yeah, hope you are able to see the screen. I'm going to put the full screen on your, yeah. Are you able to see it now?
Yes, sir.
Can I proceed?
Yes, sir, it is visible.
Okay, so let us begin. Yeah, absolutely. So let me talk with respect to the introduction of my friend. Okay, so let me introduce my friend to you. I will start my lecture by introduction, and who is nothing but the pure and poor analytical chemist like me. Okay, so he is playing with some important terminologies which are very critical in analytical chemistry: sensitivity, selectivity, separation, structure, and speed. Okay, so all these are 5 important S of analytical chemistry. And the analytical chemist always talks about this. And what is so important about all these 5S with respect to mass spectrometry is that the mass spectrometer, along with GC or LC, gives you all the 5S, including the structure, because GC alone or LC alone cannot give you structural information. But when you have a combination of GC with MS or LC with MS, you get structural information about the molecule. And then you have much better sensitivity, because you can find out the structure of a molecule at very, very low level. Even the concentration of a compound is at a picogram level, you can still find out the structure of a compound. The mass spectrometer and the chromatography combination makes it very, very selective. Chromatography is used for separation. So even if you have a complex mixture, you can separate individual components and determine the structure of each and every component which is there in the mixture. Of course, you can get the structural information, and then the speed of analysis, which is very critical in industry. You can achieve all this information with a very high speed, because today most of the chromatography equipments are high throughput equipments. They are able to separate many, many components in a given mixture very fast. Okay, so fast chromatography is coming up, and similar to that, fast mass spectrometry is also there to evaluate the molecule very precisely. Okay, of course, one has to be very careful when he is playing with this 5S, and something needs to be suppressed, and those are very critical in analytical chemistry. Most of you know about this. Sampling error needs to be reduced, the background has to be reduced, and the noise level also has to be reduced. Okay, and we always talk about sensitivity of any analytical instrument in terms of signal to noise ratio. So you can understand then the significance of noise. If you reduce the noise, signal to noise ratio will increase and sensitivity will increase. So these all the parameters are very important as analytical chemist, and that is why I just wanted to introduce this concept to you through this friend of mine. Let us begin with the kind of techniques which are available as the techniques where we have combination of mass spectrometry with other techniques. Of course, I have taken also in consideration the techniques where FTIR and NMR also are involved. But many cases, mass spectrometry is a better technique compared to other, we call them as hyphenated techniques. So compared to hyphenated techniques, GCMS, LCMS are more important, because they can give the kind of sensitivity which is not possible by many other techniques. Okay. So what is the importance? Which techniques are of importance to us? GCMS, LCMS, and MSMS. So in this talk, I will cover these topics, and then the relation of the mass spectra which you get with respect to the structure of a compound. So we'll talk with respect to structure of a compound also. Just brief history of GC, LC, and MS. As you can understand, LC was developed much earlier by Mikhail Sweat in the beginning of 20th century. 1903 to 90 was the period when Mikhail Sweat worked on the chromatography. MS also got developed around the same time by J.J. Thomson. So 1 minute, I'll just put my pointer. Yeah. So MS also got developed around the same time, but both these techniques were developing parallelly, but only after something like 65, 70 years, LC and MS got developed in 1952 by James and Martin, and within 4-5 years, you have a GCMS already existing. Okay, so we'll try to find out why it is so, and why this kind of a combination was felt necessary. Okay, let us begin with why chromatography was connected to mass spectrometry. Yes, chromatography gives you only one dimension, that is the retention time. And with retention time, we try to say that this compound may exist. So if we have a standard and we inject it in a chromatography and we get a retention time, which is a particular quality of a compound under a given condition. And if we have some unknown and which has a compound which elutes at the same retention time, we can say that this compound may be present. So we are not sure, because there is a possibility that many compounds can elute exactly at the same time. So we cannot confirm that this is the compound. And as you can see, if there are 2 compounds or 3 compounds or 4 compounds, chromatography will separate them and mass spectrometry will be able to like this. So the mass spectrometer, when it is connected to chromatography, gives you one more dimension, not only the retention time, but it also gives you molecular information. And this molecular weight is of course specific to that compound. And then if there are many compounds, you can get molecular weight information for all those compounds. Then it gives you one more dimension, that it gives you fragments. So if the molecule gets fragmented into its groups or pieces, each one has its spectra for all those compounds, and that would be able to give you a fingerprint for that molecule. It might be spectra for this molecule, it might be different molecule. Okay, if there is a third molecule, it will not be identical to that third molecule. So as the compound gets separated, you start getting the mass spectra of that compound, and you will get the molecular weight information, you will get the fragments, and each fragment which has its own mass will be able to tell you what this compound could be. And that is how the mass spectrometer helps you to finding out the structure of a molecule. Okay, so let us see how the mass spectra or mass spectrometer looks like. What are the components of a mass spectrometer? So I will quickly go through that. So these are the components of a mass spectrometer. We have a sample inlet. Now, a sample inlet could be GC or LC, or if you have a pure compound, you can directly introduce it into mass spectrometer. So there are some devices which are called as probe, which can be directly inserted into mass analyzer or mass spectrometer, and you can analyze that compound directly, provided it's a pure compound. But many a time mixture, and we need to separate those, and we have best separation technique like chromatography, which will be able to separate those compounds, and then that could become a sample inlet. So we can have a GC, LC, supercritical fluid chromatography, capillary electrophoresis, so many devices which can be put here, which will do the job of separation. And after the sample gets separation, it enters into the key components of a mass spectrometer. And those 3 key components are the ionization part, the mass analyzer, and the detector. Okay, so 1 minute. If there is any problem with, yeah, is there any problem with my connection? Hello? Hello? Yeah? Yes? Okay, yeah, fine. So we have the ionization, mass analyzer, and detector spectrometer. So whatever separated from the from equipment, it goes to the ionization, and it gets converted into ions. And these ions then move into mass analyzer, which will separate those ions on the basis of mass situation. And then those ions which get separated go to the detector. Detector checks the strength of the ion, as well as with respect to time, it will also tell you what could be the mass of that ion, and you get everything, records everything. So that is how the instrument works. So once you introduce the sample, the first component of a analyzer is the ionization part. And then this ionization part plays a very important role, because the mass analyzer can only separate the ions. If it is a neutral compound, it cannot do a separation. So you have to ionize the compound. And then there is one more requirement of a mass analyzer. That mass analyzer can only take ions on the surface. So the mass analyzer only can ionize, only can separate the vaporized ions, and then only you will get the signal. So these are 2 basic requirements of a mass analyzer. It should be, one is that whatever is coming should be charged, and it should be in a vapor form, so that you can only it will be a, remember this is a very important information about analyzer. I'm going to start from ionization part because sample inlet or LC, which are familiar with these two techniques, gas. So we will talk and go to the mark. So ionization, there are two types of compounds which can be used generally and other are non-volatiles. So volatile samples can be GC and non-volatiles or thermal are separated by LC. So we have two different techniques, one for volatile samples, one for non-volatile samples. And because of the nature of these two compounds, different techniques of ionization. So volatile samples by two techniques known as EI and CI, which are electron ionization and chemical ionization, and non-volatile samples are ionized by using different technique called, we will study only one of them or maybe two of them because they are outdated now, though it is useful technique. And then we'll talk about those are the ionization techniques which are used with LC and whatever else which are these three ionization techniques. Okay, so look at three techniques as major technique. We'll talk about a little bit about TSP and MARDI, etc. Okay, so we are going to talk about ionization. Remember, ionization is the most important. In fact, I used some punchlines to define three techniques, LC and MS. If you ask GC what you can do, GC will tell you that if you can evaporate, I can separate. If you ask LC what you can do, and this is a known punchline, which says that if you can dissolve, I can mass analyze, I can recognize. So if you know these three punchlines, in fact, you know three techniques very well. Okay, let us go ahead and talk about what is EI. And as I said, EI being used for volatile compounds, it is used with GCMS because GC is the technique which is able to separate all the molecules which can be vaporized or which can be evaporated. So for GCMS, we have two techniques, EI, electron ionization or electron impact ionization, CI, which is a chemical ionization. Okay. So let us talk about EI first and then go to CI. So in case of EI, they are bombarded onto the molecule.
So
Their
just
energy is about 70 electron volts. And with such a high energy,
Datar sir,
any
just
sigma bond also can be cleaved. Okay, so it can even break any sigma bond. So with such a high energy, you can expect molecule will get fragmented totally. But the entire energy doesn't transfer that. The fragments of the molecule, which you can use out the structure molecule. So as I said, electron ionization is a very high energetic, very high power electron energy onto the molecule. Plus radical. That means one electron from the molecule is knocked off and you get M plus radical because one electron is still left unpaired in the orbit. And because of that, it is a radical, but as one electron is lost, it is having a M plus charge. So we have formed the ion. Then because of high energy, it produces abundant fragment ions. So not only we get the molecular ion, we always get with electron ionization lots of fragmented ions. Okay, so which will reveal the structural information about molecule because each one has its own mass, and that will reveal us information about that molecule. There is something which is when the molecule is very fragile, not structural, structurally stable, you may get only fragments and you will miss the molecular ion weight of a compound. While if this is not formed because of high energy of electrons, you may miss this information for some of the molecules. So molecular weight information may not be available. One very important thing about spectra, that means every time you use 70 electron volts as a default energy falling onto the molecule, it will always fragment the same way every time. Okay, so each and every molecule will have its own fragmentation pattern, and that will remain constant whenever 70 electron volts energy is used. So if I make the measurement today, or if I make the measurement of the spectra after a month or after 1 year, or one machine or other machine, or the GCMS manufactured by manufacturer A or manufacturer B, I will get the same spectra every time for the same molecule. And that is why all the spectras, and there are commercial libraries available for GCMS, which have more than 3 lakhs of organic compounds, and their spectra stored. And one can use this library whenever he is working with GCMS. This library is in form of the database on every GCMS supplied to any user, and then it can be seen along with the compound spectra, and then you can identify the compound, or at least the library will help you to come closer to the structure of your compound. Okay, so it will help you, assist you to getting structural information. Well, so how it works. So we have electrons bombarded from the, so these are electrons going to the anode, that is GCE. So these are all vapors of the molecule which are coming. Of course, you have a lot of carrier gas molecules also coming along with it, which are not shown. And because of the bombardment with electrons, this molecule gets ionized, and then through this lensing system, it goes into the mass analyzer, which is located here. So ionization happens in one area, and the ions are then directed towards mass analyzer. There is something called as a pusher plate here, which has got a positive charge, will make ions to go in this direction. And these lenses would make them get focused onto the mass analyzer. Okay, so they don't deviate. They will get into the mass analyzer, and mass analyzer will be able to separate them. This is how it works. So if you take an arbitrary example, say ABC, and it gives you ABC excited, we are not interested in that, then it gives you ABC plus 2 electron, AB plus 2 electrons, BC plus. So one electron which is bombarding onto the molecule, and molecule bombardment. So it knocks off one electron from the bombarded molecule. So you get 2 electrons out. Okay, so that is how we are seeing everywhere 2 electrons. AB, this C is a neutral. So every time you have a fragment form, there is also a neutral form, because the bond between B and C is broken. This gets a positive charge, and this becomes a neutral, because there is only one positive charge here. So you get AB plus C. You may get BC plus A. You may get rearrangement, so AC plus, and then BC becomes a neutral. So every time you get an ion with a neutral, neutrals also help us in finding out the information about the substance. You can give A plus, like ABC, give you several fragments, and each of such fragment will accelerate
Excuse me, sir. Excuse me, sir.
acetophenone.
Excuse me, sir.
Hello,
Hello.
hello.
Sir, your voice is breaking in between. Will you please
Yeah.
see the internet connectivity?
Oh, is it okay?
Yeah, it's breaking too much. Thank you, sir.
Yeah, I will just check. It is now still it is okay, or it is still breaking, or is it okay now? Is it
And now it's
better?
come. Yeah, it's better now.
Okay, so let us see. Yeah, I hope it remains like that. Okay, so you can see this is a molecule acetophenone, and I have divided this A group is A group and C. If you calculate
Sir, we can't hear you.
demand. So that's a again a problem.
Yes, sir. In between,
Hello.
it's yes, sir. In between, it's breaking.
Yeah. Okay. Okay. Yeah, can't help it because yeah, I'm using the maximum speed connection, and still if it gives problem, I am not very sure. But then at least you are able to listen to me, and you are able to see the PowerPoint presentation correctly, or is there any problem there also?
No, no, we can see the slides clearly.
Okay, good. Okay, so fine. So if you find anything, any of the slide is not very clear to you, you not miss anything. Okay,
Yes, sir.
fine. So this is a molecular mass of this molecule, and we know it is 120. Well, of course, I know this molecule I have injected, so I know this is 120. But even if I don't know this, I can see that this is a molecular weight of this compound. Having a peak at 105, ABC, it has got fragmented to give me AB plus and C is lost. Okay, so this AB plus is 105. So the difference between these two is 15. So the loss of 15 has happened. That means it could be a methyl group. So I clearly have a methyl group. Then there is a loss between this to this is 20. So we know this is 368. So this group and this 7 and this is it becomes 120. So this could be a molecule. Then I am also able to see this 43 BC plus and A. Okay, so we have seen that in the previous slide. We have the BC plus. Okay, so we have the BC plus A, and exactly that what we are seeing here for BC plus and A77. Okay, so like that we get the information about this molecule, and when we have the library of this particular um, GCMS, we get the structure and we know the formula. It is nothing but acetophenone. Okay, so that is how spectra helps you to find out what this all these peaks, which are called as M by Z peaks, and this is a molecular weight. This is called as a base density. Is called as base peak. And what is done is we considered base peak as 100%, and with respect to that, all other peaks are calculated, their intensities are calculated, and this is called as relative abundance spectra. Okay, so this is relative intensity with respect to base peak as 100. Then not only this M by Z information at what M by Z coming, but also the ratio of this peak with respect to the base peak. If this is 100, this peak should be about 40%. If this is 100, 70 should be somewhere around 85%. So like that, important that the library takes into consideration, take into consideration not only the M by Z value, but also the ratios of to identify. Okay, so that is spectra of acetophenone using a GCMS. Okay, fine. So we quickly go to the next technique, which is called as chemical ionization. Now, I have made a remark in the previous slide that when the compound is 100% a fragile compound, not structurally stable, we may not get ion, not know what is the molecular weight of that compound. And if I'm working on a compound which probably is not there in the libraries, that is those 3 lakhs of compound, it is out of those libraries, then it is very difficult for me to judge from the EI spectra that the highest molecular weight which I'm seeing in the spectra is the molecular ion. It may not be. If the structure is fragile, I may not get a molecular ion. So I need to confirm that what is the molecular weight of this particular compound, because without molecular weight I cannot really find out any information. Molecular weight is very essential. Like jigsaw puzzle, if I give you some 100 pieces and tell you to assemble a picture out of that, and a picture can be made by using those 100 pieces, it is very difficult to assemble those 100 pieces and make a picture unless and until I give you the picture how it looks like. Okay, so if I have a picture, a photograph of the actual picture, and I tell you that this is the picture which we want from these 100 pieces, you will find it very easy. If you have the molecular weight information, you know of your pieces which you have and how to reach that boundary, and you can make a structure which is
Sir,
very
your voice is
easily
cutting again.
from the fragments is of ionization information.
Uh,
Yeah. So use reagent gas and inserted in the ionization chamber, which gets ionized first. Now, you have a different kind of reagent gas. Okay, so you have a reagent gas, and then the kind of spectra which you get gas and slightly different, and because of that library for CI generally weight information only. So let us look at how you get the information like. Okay, so you have the same EI, only the thing is that now I'm introducing a methane molecule inside. I'm taking just one example of methane molecule. You can have anything else. So this is the methane molecule which gets ionized molecules are coming, which will also get ionized now, and then they are interacts with the molecule, and in the the molecule gets formed. You do not get a molecular ion directly. You get a protonated molecule. Let us see how it works. Okay. So you have a methane gas, bombardment of electron. CH4 plus loses one hydrogen as a neutral to give 3 plus. Then CH4 plus interacts with another neutral CH to give me CH5 plus, and this is the metastable ions with the molecule to give me MH plus, a proton atom, and that is how the molecular weight can be measured. Because if you get this information, you know the molecular weight is 1 unit less than whatever you see in the spectra. Let's look at what exactly happened ionization spectra with that 70 electron volts energy. These are two molecules. One is and both the molecular weight 277 and 275. I'm not able to see the molecular weight. The molecule being fragile, it breaks, and you can see the molecular weight of the molecule. By chemical ionization, get way MH weight. I'm getting a peak at 278. So if I subtract weight of proton, 6 is ion weight. Actual molecular weight is 275. So the chemical ionization helps you to find out the structure a molecular weight of molecule, and as you will never miss a molecular ion chemical. You will always get a molecular weight information, and that's the advantage of chemical ionization as an accessory to the electron ionization in many places. So positive ion chemical ionization gives you a lot of advantages. Molecular weight information is definite. It gives increased selectivity. Selectivity affected by various reagent gases gives orthon and direct ion for confirmation. Technology right now, because of the time which I have, I will miss some of the note of for you to study those. Okay. Now we quickly go to the LCMS. Now we have a LC where we do the analysis of non-volatiles or involatiles or thermally labile. GC is used for the compounds which can be vaporized or evaporated. Now there is a main difference between these two techniques in one way that GC can be used for only 10% of known organic compounds, while LC can be used for more than 90% of the organic compounds. Okay, so that's the main difference between the two. So if GCMS can LCMS also should be able to do a much better job. So people were frantically looking for having a good LCMS system, but they realized as LC is used for involatiles, that's going to be a main challenge because we have already understood what mass analyzer requires. Mass analyzer requires a sample to be in a vapor form and ionized. Now, how to convert these involatiles will degrade or they will decompose before their boiling point. So people were really trying to find out to take involatiles into mass spectrometry, but that was a very challenging kind of a task. So it was a difficult task for some time, producing a variety of innovative techniques. Now we have proceeded. So people had all these techniques like FD, field desorption ionization, fast atom bombardment, secondary ion mass spectrometry, and also thermospray and particle beam and so many more. Okay, all these techniques are now obsolete. Nobody is making these techniques because we have now much better techniques. So to understand what is the significance of why they became discontinued or why they stopped, and a little bit of that. Well, to understand that, we have to first understand the concepts of having LC connected to MS. Okay, so I put a cartoon. I like to draw a cartoon. LC is and for LC because in phase and works in a
Excuse me,
how
sir.
to take samples which are in liquid phase. Yeah.
Sir, we can't hear you properly.
Again, the problem with the
Yes,
noise.
yes, sir.
My goodness. Now, no, I'm only trying to switch. Change the position of my dongle, and I'm not doing anything else because I do not know if its position is important.
Now it's coming proper.
Okay, but then with that, yeah, now it is okay.
Yeah, at the moment it's okay.
Hmm. Okay, is it better now?
Yes, sir.
Okay, has it improved a little bit?
Yes, sir. It's improved.
Okay,
Thank you, sir.
so yeah, okay. So LC mobile phase generates, yeah, so this is one reason that MS requires LC sample is in a liquid phase. Now, how to convert this into a gas phase without decomposition is a problem. If you try to vaporize the sample, it will decompose. And that is why LCMS was found to be very difficult. Okay, people felt that the good LCMS is never possible. Okay, but then people worked on that. One more reason why people felt that LCMS is not possible because of the mobile phase. Mobile phase in LC is just, if the solvent being a low volatile solvent, I mean, it can be easily vaporized. Still, the compound which are soluble in the solvent cannot be vaporized. Okay, so again, there is a challenge. But then more of a challenge is that the LC mobile phase generates too much amount of gas to be handled by vacuum system. Now, GC is connected to MS. It also has a vacuum system, but GC has a carrier gas, which is like helium, which is going into the vacuum system of a mass analyzer along with the sample molecules. Now, when the gas is going to the vacuum system, it can be easily evacuated because if 1 ml of a gas is entering into the vacuum system, at NTP, it would be very close to 1 ml. Okay, but when we have 1 ml of mobile phase, and if we convert that into vapor, it will generate too much amount of gas. For simplicity, if we use 1 ml of water as a mobile phase, okay, so 1 ml of water, if that is the kind of a flow rate per minute, which is a standard flow rate in any normal HPLC system, how much amount of gas it would generate if you really calculate by using Avogadro's hypothesis, because we know that 1 gram mole of any substance will generate 22.4 liters of a gas at NTP. So 1 ml of water means 1 gram of water would generate 22.4 divided by 18, it will come to about 1.2 liters of a gas. And if this gas gets entry into the vacuum system, and that too at every 1 minute, the vacuum system cannot handle that much amount of a gas. Compared to, in case of a GC, we are introducing 1 ml of a gas. Here it is 1.2 liters, that is 1200 ml of a gas. So it is very difficult task. Okay, so because of that, people felt that LCMS may not be possible. Now people worked on that, and there were of course a lot of historical methods, but now we have a lot of modern methods which have uh, come out of this particular difficulty, and now LCMS is possible. Okay, so I'm just going to look at one technique which is outdated. So it is called as a thermospray technique. So it is a first widely used LCMS interface. So it was commercially available. There were LCMS systems somewhere around 1970 to 1990, which were using thermospray as the interface between LC and MS, which could ionize and which could combine LC to mass analyzer. Okay, flow rate, nominal flow rate, which generally LC is using, good for semipolar compounds. I would put semipolar, produces M plus H ion. So again, a protonated molecule, and maybe also M plus NH4 ion because ammonium acetate is used as a buffer. So what is done here? HPLC eluent is passed through a high temperature. So it is to make a spray. So nebulized at high temperature. So you get a thermal spray, okay, or heat, which is used for making a spray. And then because of that thermal heat which is provided, it can create some problems for labile compounds. And there are some problems with respect to blocking of the nebulizing needle. And it is of course not commercially available today. So it is something like that. So you have HPLC flow coming through the heated portion, and it is nebulized to give you spray. And then you have EI filament. So you do the ionization by using EI like a GCMS. So all the vapors which get generated, they are ionized. They are pumped by the pump here, and the ions which are produced, they will get entry into the mass analyzer, which is at the diagonal at 90 degrees to the flow of the vapors which are generated. Now imagine if I have a generation of 1.2 liters of a gas, lot of it can enter into the mass spectrometer area, and that can give you a huge background and will create a problem, because pumping of that, because you require 10 raised to minus 5 millimeter of vacuum in the case of a mass analyzer, and to create that kind of a vacuum is a very difficult task. So because of that, this kind of interface was not really very useful. There was another interface which was developed, which also worked on the same way. You have a helium and the LC flow are nebulized together to form a spray, and then there are two jets through which the gas generated, vapor generated, as well as your molecules are passed. It is assumed that molecules being heavy, they will go straight, and the mobile phase along with helium will diffuse into this area and pump separately, and the molecules plus the remaining amount of mobile phase vapors will go here. You have again an EI filament which will ionize, and the mass spectrometer will be able to measure those ions which are coming in this direction. Okay, so similar to thermospray, slightly different because of these kind of skimmers or jets which are used here. So because of that, there is some restriction of the mobile phase which is getting generated in this area. It worked better, but again it is discontinued, okay, because of the reason that so much amount of gas gets entry into the mass analyzer. Then I'm just going to talk a little bit about MALDI, because of the reason that it is very popular as a technique, and many of you, those who are in the biological field, they know about what is called as Multitop. So MALDI is one of the technique which is used in protein analysis and gives you structure of proteins and peptides, etc. And it is a very useful technique for proteomic studies. Okay, so I'm not going to get into that in a detail. So it is why MALDI? Because when you have proteins in biological matrix, you have a lot of salts accompanied that, and it doesn't affect, the salts do not affect the MALDI experiments. It has lower practical detection limits, so it can go very easily to picomole measurement of a protein in a given sample. Easier to interpret spectra, you get a direct molecular weight information of a protein. It is very quick and easy. It has higher mass detection, that is more than 500,000, more than 5 lakh molecular weight proteins can be analyzed by that. And it has a very high throughput, and that's the advantage. You can analyze more than 1,000 samples per hour. Okay, so that's the great advantage of a Multitop, and that is used in protein, peptides, all the biopolymers, polysaccharides, nucleotides, and all such kind of analysis. This is the kind of spectra you get. You can see the molecular weight here, 66,000 molecular weight is possible to be analyzed by this. Okay, so imagine the MALDI as an ion source is capable of taking a molecular protein with such a high molecular weight into vapor phase and then ionize it, and the mass analyzer is able to separate such a huge molecule, which at one time nobody thought that these kind of source would be available, and it would be able to take a protein which has a molecular weight of even 1 million would be possible to be analyzed by a mass spectrometer. Okay, so that's the beauty of this technique. These are two scientists which are responsible for generating these two ionization sources. One is the electrospray, which was developed by John Fenn, and MALDI was developed by Koichi Tanaka, and both of them got the Nobel Prize in same year 2002. And they developed two different ionization sources which could take high molecular weight protein or organic samples into the mass analyzer without breaking them. Okay, so that's the beauty of it. So it is said that these two scientists provided wings to the elephant so that elephant could fly into the mass analyzer. Okay, so we will talk about the electrospray which was developed by John Fenn. Okay, so how it works. So in case of electrospray, we have the same kind of a nebulization, and we have the HPLC flow coming through the nozzle or a needle, and this needle has been provided with some temperature, not very high temperature, maybe up to maximum of 250 degrees centigrade. But what is more important is positive charge, because high positive voltage which is applied here. And these droplets have positive charges. And everything, this nebulization is not happening in the vacuum system, it is happening at the atmospheric pressure. So that is why this technique is called as atmospheric pressure ionization technique. So now you have nebulization which is occurring in the atmospheric pressure. Solvents will evaporate. Molecule which is present in the solvent as a drop, it will have a positive charge. And now what happens? The droplet will start shrinking because of the flow of nitrogen gas in this area. So the droplet would shrink, it will become smaller, but the positive charges sitting on the droplet will also start coming closer together. Now positive, positive, there will be repulsion. So they will start repelling each other. Now, there is one more force acting on the drop, which is the surface tension force. So there are two forces acting on the drop. One is surface tension force, other is repulsive, Coulombic repulsive forces. These two forces are acting against each other. The repulsive force, the Coulombic repulsive force, would try to go away from each other because all of the positive charges are coming closer together. So at one moment of time, the repulsive forces will become more stronger than the surface tension force. The drop will shatter into small droplets, and finally a molecule which is sitting within the drop, because molecule is always solvated molecule, it, which is sitting in the drop will come out, and the charge will automatically get transferred to the molecule. It comes into vapor and gets entry into the mass analyzer. So that is how the sample enters into the mass analyzer, an analyte molecule enters into the mass analyzer through three phases of vacuum. Here you get a vacuum of -1, here you get a vacuum of -3 by using a mechanical pump, and here you have a turbo pump which will assure you a vacuum of 10 raised to -5, which is required for mass analyzer. Okay, so that is how the thing happened here, and most of the solvent which is there gets out because of the flow of nitrogen gas out of here, and it is not able to enter into this area. So there are two models which are said are working inside the ionization. Charge residue model: as the drop shrinks, positive charges start coming together, it shatters, and finally the solvent which is around the positive molecule, along the molecule, will come into the vapor phase, and the charge on the drop gets transferred to the molecule. It becomes positively charged and enters into the mass analyzer. So there is a model called as charge residue model. Other one is called as ion evaporation model. As the drop shrinks, one ion evaporates from the surface and the charge density here reduces. So drop can sustain. As the drop shrinks further, one ion again evaporates and the charge density reduces. So that is how the ion evaporation model is suggested. Okay, and these are two models which talk about the theory of electrospray ionization. So this is how the electrospray is happening in this fashion. This is the charged capillary, and the droplets will be charged, they evaporate, and the ions, H plus ions, that is protonated ions, enter into the mass analyzer. So generally it is orthogonal kind of a spray. So most of the mobile phase molecules go into uh, by the flow of nitrogen, and only ions of interest enter into the mass analyzer because of the cone voltage which is applied here. Okay. So electrospray summary: ESI is an atmospheric pressure ion source. Smaller molecules may be singly charged. High molecular weight samples become multiply charged. For example, polymers, proteins, and peptides and oligonucleotides, because on the drop there are many positive charges sitting. So if the molecule is capable of taking more protons from the solvent, which is a protonic solvent like water or acetic acid or formic acid which is added there, it will take more number of protons and can become a multiply charged. Okay, so there is possibility that high molecular weight compounds may get multiply charged, and molecular weights up to 1,50,000 Daltons can be measured accurately by this. Okay, so that's the great advantage. So we quickly move to the another method of ionization: atmospheric pressure chemical ionization. Now, electrospray ionization is used for highly polar compounds like protein, peptides, etc. Many pharmaceutical compounds as well. many phytochemicals as well. But APCI is used for some semipolar compounds. So we want even these compounds to get ionized. And for that, we use a technique which is called as APCI. How it works? So here it is slightly different because the molecular weight range of these semipolar compounds is less. They are up to about 1,000 molecular weight compounds, but not very uh, thermally stable. So we heat the eluent at high temperature of 450 degrees to 500 degrees. Being the sample molecules being in the solvent, they do not get a direct impact of the heat. But then whatever comes out are all in vapor phase. Okay, so your molecule is in vapor phase, your solvent is in vapor phase, but in the atmospheric pressures, all of them are in atmospheric pressure. Then there is a corona discharge needle. So we apply a high voltage onto the tip of a pin, and high voltage cannot sustain onto the small area. So it discharges, giving a plasma or a corona. And the heat over here will ionize solvent molecules. So you can see SH plus, which are the solvent molecules. And these solvent molecules will give a proton to the molecule of interest, and it will form MH plus, and then it will get entry into the mass analyzer. And most of the solvent molecules will go out because of the flow of nitrogen in this area, because everything is happening here in the atmospheric pressure. Okay, so the molecules only enter under vacuum, which are heavier and which are pulled by the vacuum over here. They enter into the mass analyzer. So APCI, multiply charged ions are rare, more tolerant to salts, less adducts formed. So I'm not explaining all these terminologies in the time available. Used for smaller pharmaceutical compounds, steroids, lipids, etc. Better with normal phase solvents than ESI. So ESI, you require always reverse phase chromatography, so highly polar solvents. This being used for semi-polar, you can tolerate some of the solvents like isopropyl alcohol, etc. APPI is the atmospheric pressure photoionization, which is used for very less polar compounds. So to the extent non-polar compounds. Okay, so it is a different technique where we are bombarding photons onto the molecule, and because of the photons, some molecules may get ionized. Okay, so there are two versions. One is called as direct APPI, other is called as dopant APPI. So M, when it is bombarded with ultraviolet radiation, it may directly get ionized. Or if the solvent used for this molecule is a protonic solvent, then it may give you MH plus. But generally, when the compounds are non-polar in nature, in case of APPI, we generally end up with M plus ion. Very rarely we get MH plus ions. Many compounds do not directly get ionized by photons. So what is done? We use some dopant molecule, which we are sure gets ionized by bombardment of ultraviolet radiation. So by bombarding ultraviolet radiation, this dopant molecule like toluene will get ionized. And then in this molecule then ionizes the molecule of interest. And then it may form MH plus if the solvent is polar, like protonic solvent, or it may form M plus if it is a non-polar solvent. So that is how dopant APPI or APPI works, and it gives you the ionization of non-polar compounds. Now let us look at some of the techniques which we have studied. So if we use EI, it is used for non-polar compounds and molecular weight range is only about 800. If we have not studied this, but this was one technique which was used earlier called as fast atom bombardment, which can go up to something like 5,000 daltons. Okay, so it goes up to somewhere around 5,000 daltons, and it can take up a lot of polar compounds like peptides or some sugars, etc. Okay, but molecular weight range was only about 5,000. Then we have a TSP, which we have studied today, and it can go up to 1,000 molecular weight range, and it is used for semipolar compounds. Then we have APCI, which is also used for semipolar compounds. Molecular weight range is close to about 1,000. So you can see on one side non-polar, one side highly polar. So APCI is useful for semipolar compounds. Then we have APPI, which is used for which is for non-polar compounds, molecular weight range is about 500 to 600. And then lastly, we have the ESI, which goes up to 1,50,000 molecular weight, and it takes care of very highly polar compound, some of the semi-polar compounds. And that is how we have these three techniques, ESI, APCI, and APPI, which are all atmospheric pressure ionization techniques, which can take care of highly polar, semi-polar, and non-polar compounds. And that is how we have a true solution available for LCMS, which gives us sensitivity up to picogram or femtogram level. Okay, so not never possible by LC alone. And that is why these techniques have become popular, so popular, that today LCMS is there in every pharma industry, in many research labs, and even in Mumbai University, we have, I think, LCs. We have, LCMS in Bombay. People have now started buying LCMS. So you will find a lot of uses of LCMS systems because of the kind of sensitivity it can give, kind of structural information it can give. And now LCMS has become very, very successful. I thought of drawing another cartoon which shows the effect of atmospheric pressure. Cock in the previous picture has compromised now, he said, but I can marry duck. Duck can exist in water as well as in atmosphere, and that is how the marriage is successful. Doesn't say quack quack, doesn't say chick squack. So we have completed the ionization part. We'll enter into the mass analyzer soon. Okay, so I'll not go through this slide. 1 minute. Sorry for the interruption. Okay, are you getting my voice clearly now, or there are some problems?
So it's clear now.
No, okay. So we are now going to talk about the mass analyzer. Okay, so ionization part is over. We are entering into the mass analyzer. Now, how the mass spectra are produced? Ions are produced in the source and are transferred into mass analyzer. They are separated according to their mass to charge ratio in the mass analyzer. For example, quadrupole, ion trap, time of flight are different mass analyzers. Ions of various m by z value exit the analyzer and counted by the detector. Okay. So what mass spectra gives you? It is a chemical fingerprint. It contains molecular weight information generally, structural information mostly, and also quantitative information, which is very important because with GCMS and LCMS, you can do quantitation up to femtogram level very easily. These are all different types of mass analyzers which are used: magnetic sector, quadrupole, ion trap, Fourier transform, time of flight, and there are a lot of hybrid MSMS instruments. We are going to talk about that. But then to cover all of them, it's very, very difficult. So we are going to cover only few of them. Of course, one is definitely quadrupole, which is used in 90% of the applications. People use quadrupole mass analyzer. Okay, so we'll talk about that. And we'll talk about time of flight, which is used especially for high molecular weight compounds like proteins, peptides, etc. So we'll talk about that also. So we have to talk about two types of mass analyzer here. One which is giving you low resolution, other which gives you high resolution. Now, what is the difference between the two? Let us try to understand by this table. Now, these are the elements which are mostly there in all the organic compounds, common elements, and these are their nominal masses in integer. Okay. In case of exact mass, for carbon, we always assume it is 12.0000. Carbon 12 is always considered to be 12.0000. While all others, we assign their atomic weights on the basis of comparison with carbon 12. So hydrogen is 1.0078, oxygen is 15.9949, nitrogen is 14 points, so like that. So we know these are the exact masses. Now, we have two types of mass analyzers. One, low resolution, they consider the atomic weights like this, and whatever molecular weight comes by using these atomic weights, are given by those mass analyzers. Like quadrupole will give you molecular weight based on these masses. While the high resolution machine like time of flight, magnetic sector, there are new instruments like Orbitrap, and there are many more high resolution machines which are coming up. They will give you accurate mass on the basis of these atomic weights. So you get molecular weights up to fourth decimal, and that gives you much better structural information compared to these molecular weights based on these atomic weights. Okay, so low resolution machine gives you the atomic molecular weights on the basis of these atomic weights, and the high resolution machine gives you molecular weights on the basis of these atomic weights. And these are average masses considering all the isotopes. So carbon has 12 and 13, hydrogen has hydrogen and deuterium, oxygen has oxygen 16, 17, 18. So when we consider that, we get these atomic weights. Okay, and these are called as average masses. And chlorine has 35 and 37. So chlorine average mass is much higher compared to the other atomic weights. Okay, bromine would be 80 instead of 79, 80 point something. Okay, so that is how the average masses are the ones which we use in giving the molecular weight information, which is used to prepare a molar solution. Okay, so we use these masses, but the mass analyzers give you either this or this. So remember that. Okay, so we come to the first mass analyzer, which is called as a quadrupole mass analyzer. It has got 4 rods, and these 4 rods are approximately 8 inches, or say 20 to 30 centimeter in length, and about 8 millimeter, 6 to 8 millimeter in diameter. Okay, so they are very compact. I can hold this mass analyzer very easily in my hand. Okay, so I will show you the mass analyzer, how it looks like. So I have made one which is very uh, similar to what exactly is found out. So this is the mass analyzer which I have, and it can be held easily in my hand. Okay, so this is, each rod will look like this. Okay, so this is the rod, this is the diameter, and this is as per the one which is actually used in any instrument. Okay, so it is so compact. Okay, so this mass analyzer, we use the uh, DC and RF voltage, and by using DC RF voltage, I will just stop video. Okay, so by using DC RF voltage, I am able to take the ion to the other side where the detector is. So ions are coming from one direction. I go on scanning DC RF voltage in such a way that at a particular DC RF voltage, one ion gets stabilized and go to the detector. At that DC RF voltage, all other ions will go out. They will never be able to reach the detector. Are you able to get my voice clearly? Is there any problem?
Yes, it's okay.
No? Is it
Yes,
okay now?
yes, it
Yeah,
is
okay.
okay.
So at one particular DCRF voltage, one ion gets stabilized. At that voltage, other ions go out. Maybe at some other DCRF voltage, the ion which is shown by red or orange color will go to the detector, and at that time, the ion which is shown by green color will go out. Okay, so
Excuse me,
at a
sir.
particular
Excuse me,
DCRF
sir.
voltage,
Excuse me, sir. So
yeah,
it's now it's too much disturbance at your end. Like we can't hear you.
you
Some
can't
other,
hear
yeah,
me.
other sound is also coming.
Other sound is coming.
Yeah.
Okay, I will just close this. Yeah. Okay. Is there any other background coming now?
No, sir. It's
No,
fine.
now it is okay.
Yes, sir.
Yeah, okay. So we have a DCRF voltage which will control the movement of ions, and we scan this voltage continuously so that one by one ion will go to the detector, and all the ions of different M by Z will be measured by the detector as they come out. Okay, as they come out from the ionization source, get into the mass analyzer, we measure them. And this scanning is so fast that it is scanning at the rate of something like 20,000 Daltons per second. Okay, so in 1 second, we can scan 0 to 20,000 molecular weight compounds. Okay, so if I have ions from one mass to 20,000 mass, all of them will be scanned in just 1 second. Okay, so you can imagine the scanning speed. And that is why if I have a compound, if I'm using this quadrupole for the molecular weight up to 2000 molecular weight or 2000 Daltons, that means if the scanning speed is 20,000 Daltons per second, in 1 second, the molecular weight of up to 2000, I'll be able to scan 10 mass spectra in 1 second. So 1 to 2000, 1 to 2000, 1 to 2000, I can do 10 times in 1 second. That means if I have a peak coming from chromatography, in 1 second on that peak, I'll be able to take 10 mass spectra. So it is so fast. So as soon as the compound eludes from the column, I am able to measure the mass spectra on that. And if the peak width is just 1 second, that means peak has started coming, gone up and come down. Okay, so as I counted one, the peak is over. And within that count, I'm measuring 10 mass spectra on that peak. So it is very, very fast. It is what we call as on-the-fly analysis. It does the analysis very, very fast. 1 minute, please. Okay, sorry for the interruption. It is taking unnecessarily, this particular slide is taking too much of a time. The courier also had to come at this time, okay, when nobody is there at home. Okay, sorry. Fine. So this is one advantage, that I can scan the compound very fast because of very high scanning speed of the quadruple mass analyzer. There is one more advantage of this, that as I scan the DCRA, I can also do one thing. I can keep a DCRA voltage constant so that only one ion goes to the detector all the time. Okay, so it will never miss it. So when I operate quadrupole in this particular mode, by keeping DCRA voltage constant, I will be able to do the quantitative analysis, because I will continuously be able to monitor this particular ion, say green ion, and I will never miss it. Okay. So the mass analyzer can be operated in two modes. One is called a scan mode, where I can measure all the ions which are coming of different M by set. And when I want to do quantitation, I know what compound is present, I know its mass, so I'll keep the DCRA voltage constant for that mass, so that that particular ion goes to the detector all the time, and I'll get much higher signal, and which will be able to give me better quantitation. And when I operate this in this particular mode, it is called as single ion monitoring mode of a quadrupole. So single ion monitoring mode. So in these two modes, I can operate the machine. Scan mode is used for qualitative analysis. Sim mode is used for the quantitative analysis. Okay, so that is how the quadrupole can be worked. Okay, fine. So I will go to the next slide. I'm not sure what is happening. Why I'm not able to go to the next slide. Oh, yeah. Okay, I'm not going to spend more time on ion traps, so let me forget about that because of the time. I don't know how much time is left for me now. Hello?
Says 15 minutes more.
Is there any, what is the time limit for me? 15
That,
minutes more. Okay,
yes, sir.
fine. So that is why. So I'm, yeah, so time of, hello? Yeah. So this is another mass analyzer which is very popular, time of flight, and that is because it can give you high resolution. So it can give you molecular weights up to fourth decimal level. Okay. So how it works? So we have a tube which is called as a flight tube, which is about 50 centimeter to 1 meter in length. Okay, so it is quite long compared to the quadrupole, which has a length of about 20 centimeter to 30 centimeter. Here it is about 50 centimeter to 1 meter in length. And we have something called as a pusher plate here. So this plate, I can put a positive charge, a pulse of positive charge. So when ions come, they come in front of the plate and I give a pulse of positive charge to that. So because of positive repulsion, the ions will start moving in this direction. There is a detector at the other end. Okay, so what will happen? The ions will move as per their velocities, and the velocity would depend upon the mass. Okay, so the one which has got low mass will move very fast because it has received the same energy. The one which has got high mass will move slowly, and that is how the separation would occur. Okay, so the ions get separated. As the ions come to the other side, all the ions have come to the other side, you apply another pulse of positive voltage here. So whatever fresh ions are coming here, they will be moved. And what you measure is the time taken by the ions to go from this place to this place. And that is how this mass analyzer works. So you need to calibrate. Even the quadrupole and all the mass analyzers require something called as mass calibration or tuning with the known sample with known masses. And once you calibrate it, then it works beautifully for all the masses which you have. So mass calibration is very necessary for the mass analyzer. It is same thing which is required in spectroscopy also. You require to calibrate the spectrophotometer for the wavelength calibration. So same thing here, the x-axis M by Z as well as y-axis the detector output needs to be calibrated. Well, the time of flight is never used as a single tube. It is used as with a reflectron. So the ions come in this direction and go back in this direction. Okay, so you are multiplying the distance by 2, so 1 plus 1. Okay, but in addition to that, there is something which is done here. There is a reflectron here. So we are providing the grid of potential here. So what happens? The ions which are moving very slow. Now, if you understand here, when the ions come in front of the plate, they are never going to be in a line. Okay, so some ions, because in the vapor phase, they can be very close to the plate. Some ions can be away from the plate. Some ions could be here. Some ions could be here. So when the positive voltage is applied, depending upon the distance of the ion from this plate, they will start moving. Now, if all the ions have exactly same mass, they are supposed to go to the other side at the same time. But that doesn't happen because of that initial play. So the ions which were very close to the plate will start moving fast. The ions which were away from the plate will start moving slow. So they have different energies, and that energy has to be compromised somewhere. So what is done here is that the ions which are moving very fast will go deeper inside and then get reflected back because of this potential, while the ions which have less energy will get reflected back much earlier because of this reverse positive voltage which make it turn back. And both the one which was moving fast and the one which was moving slow will meet together and go to the detector at the same time. And that is how you get this separation. The ions which are moving very fast, they have the same mass, which do not go together at the detector end. We make them reach the detector at the same time. So that is what happens. If I have a single flight tube, I get the peaks like that, or if it is a single compound, still I get with the known molecular weight compound, I get spectra like that. But when I use a reflectron, I get a very sharp peak, and that shows that the diffusion has not happened here compared to here. Okay. So TOF has many advantages. The best advantage is that it has a high mass range. That is why it is used with MALDI, where we can move molecular weight. Adaptable to any ionization source, good for proteomics application, etc. Okay. Now we'll go to another area which I have to complete before I complete my talk. LCMS, all the technique like electrospray, pressure chemical ionization, atmospheric pressure photoionization, all are the soft ionization techniques. That means you do not get fragments. Now this is a compound which is called as salbutamol, and its molecular weight is 239. Proton is added, so I'm getting a molecular weight of 240. I have fragments here. So I do not know. If I only get this information, I cannot say this is salbutamol unless I am able to fragment it and look at the fragments of this molecule. So fragmentation is must, but the ion source is not able to give me the fragments. In case of GCMS, when I use that EI, electron ionization, 70 electron volts energy, I get lots of fragments because it was a hard ionization technique. While all the atmospheric pressure ionization techniques are soft ionization techniques, I only get molecular weight information. I need to fragment it to give me structural information. And that is possible by using MSMS. So that is why we are coming to a technique which is called as MSMS. Okay. So we have to use something called as collision-induced dissociation for LC-MSMS. So what we do, we have a quadrupole which is used between the two quadrupoles. So there is one quadrupole here. This is a quadrupole which is used as a collision-induced dissociation cell. And then I have another quadrupole here. Okay. So what I do, whatever ion I have selected for fragmentation, say salbutamol, which comes here, I give a collision energy to it. Okay, that means I make it vibrate in this area vigorously. So it vibrates here very vigorously. And then there is a leak of argon or nitrogen gas from the other side. So what happens? This vibrating ion collides with argon or nitrogen atoms or molecules and fragments. Breaks because of the collision. So what happens? This ion breaks to give me fragmented ions. Those fragmented ions, I push them into third quadrupole. So this is one quadrupole, this is second quadrupole, and there is one more quadrupole here. And that quadrupole will separate those ions to give me the fragments of this ion, which will reveal me the structural information. So all the mass spectrometers which are used with LC, they are mostly LC-MSMS, because without MSMS, you cannot get a fragments in LCMS. Okay. So we have a device like this. So this is a hardware of LCMS. I mean, you have the ionization source, say Electrospray. We have the Q1, that is quadrupole 1. We have a collision cell. We have another quadrupole, we call it as Q3. It does the job of the ion which have selected in Q1. Let us see what happens. I have a Q1, I have number of molecules which are coming into Q1. I have number of molecules which are coming into Q1. Suppose I want to fragment this ion. So what I will do, I will only select Q1 for SIM mode. So single ion monitoring mode. So I only select this ion. So comes in. So I have removed all other ions. So this ion comes. This ion will get into collision cell and will fragment. So it has broken into pieces, and then these pieces get into the third quadrupole, and third quadrupole will give me, uh, then they will go to the detector, and detector will give me mass spectra of these ions. And then that will tell me about this particular ion. Okay, so which is original ion, which is called as a molecular ion, which is called as a precursor ion, or earlier days, which used to be called as a parent ion. And these ions as a ion or daughter ions or fragmented ions. And these fragmented ions give me structural information about this molecule. Okay, and tell me the structure of this particular molecule. Okay, so and there are so many other scan events which are possible by this. I'm not going into that. Where I have a quadrupole, then I have a collision cell, and this is that reflectron time of flight mass analyzer, which gives me high accuracy. So what I can do is whatever ion which is generated, I will select the ion in a SIM mode, pass it on to the top. So I'll get a molecular ion up to fourth decimal molecular weight. Then I select that ion, fragment it here, and all the fragmented ions will go to this top, and I will get the fragmented ions up to fourth decimal level molecular weight. And that would give me a very good information about the structure of the molecule. And that is what we are going to So this instrument is called as a Q-TOF instrument, where quadrupole is the first mass analyzer, time of flight is the second mass analyzer. In between there is a collision cell, and which will be able to give us the fragmentation of the ions which are generated in electrospray ionization. Okay. So we have detectors, and we are not going to talk about detectors. We are going to have photomultiplier tube or electron multiplier or microchannel plate as detectors. We have a lot of GC applications in various areas, which remain same as application of GC. So GCMS and GC applications are same. Only the advantage is that GCMS gives you 1,000 times better sensitivity than GC alone. Okay. Well, we have a MS interpretation part. I do not know if I can take another 5 minutes or so, and I will try to explain the fragmentation. You have sample to be analyzed. You have to process in this way. Run the spectra you get against a database if available. Don't stop there. Obtain a high resolution spectrum if possible. So you get molecular weight up to 4 decimal level. This will help to constrain the elemental composition. So you can, because of the high resolution molecular weight information, you can get elemental composition. That means how many carbons, how many hydrogens. CHNOS analysis will be available. And follow the standard interpretation procedure to make sure that you identify. That means you will be able to identify based on the isotopes you have. Isotopes for structural information. Isotopes have different masses, so they give you a spectra in the mass spectra. So carbon 12 will give you a position at carbon 12. Carbon 13, which is 1.1%, will give you a peak 1 unit higher than the actual molecular ion because of carbon 13. So when you look at the spectra, you get information about the peak. I will show you peak. This is peak. So you always get 1.1% of every carbon. You will get carbon 13 peak. So if there are 10 carbons, you will get a carbon 13 peak, having that is how 1.1 will be the carbon 13 peak height. And if you know the carbon 13 peak height, you can calculate number of carbons in given molecule. So I have done exercise here. In this molecule, number of carbons are 8 because they cannot be 8.2. So number of carbons in this compound are 8. So that is how one can calculate from the isotopes number of carbons. Similarly, bromine has two isotopes, bromine 79 and bromine 81. And because of that, CHBr3 kind of a compound, because of 3 bromines, give you such a complicated M+2, M+4, M+6 kind of a spectra. This is because of 2 bromines, 1:2:1 is the ratio. So like that, you get a lot of information from the isotopes also. Okay. So here you can see there are 2 chlorines. They will come in a ratio of 9:6:1. Okay. So 146, 148, 150. And there is a carbon 13 peak here between the two, and which will be, because there are 6 carbon in this compound, it will have a height of about 6 into 1.1. So 6.6%, so close to somewhere around 7. And that can tell you that this compound has 6 carbons in it. So isotopes can give you a lot of information, and they are very useful. Okay, so like that, various possibilities of M+2 peaks, 2 chlorines, they will give you peak in the ratio of 3x plus 1 bracket square, so 9:6:1. Bromine, 2 bromines will give you x plus 1 because 1:1 ratio bromine is there. So you can get 1:2:1. So like that, you can calculate number of peaks which you will get because of various isotopes, and that will help you to find out the structure of the compound. Okay. So here I have shown you one example. If I have 2 chlorines and 1 bromine in a compound, 1:6:1, how they will look like, and you will get 9:15:7. So I'm not going into details very about the structure when compound has definitely one nitrogen or odd number of nitrogen. So it is very easy to look at the molecular weight, and if the molecular weight is odd, you are sure that the compound has nitrogen. When the molecular weight is even, it could have zero, it is you can't specify that the compound has nitrogen. But when it is odd, you are sure that the compound has a nitrogen in it. Okay, so you can able to compound by that. Okay, so there is something called as the fragmentation process in GCMS, which gives you a lot of information. And one such thing is the McLafferty rearrangement. Okay, so I'm not again going to talk more about that, but McLafferty compounds like aldehyde, when you have an aldehyde with a gamma hydrogen like butanol. So if we write a butanol like this, hydrogen at a gamma position, so you get enol ion at mass 44. So this is a typical of a aldehyde if that has got ion at gamma hydrogen at a gamma position. Okay, so aldehydes will give you 44. Ketones, methyl ketones will give you mass at 58. This will be a base peak in the spectra. If it is carboxylic acid, you get a peak at mass 60, which will be a base peak. If you have a ester, it will give a peak at mass 74. And generally, these are very common compounds in essential oil. And essential oil has lots of components which have aldehyde, ketones, esters, etc. And you can find out the structure of those many compounds by using this McLafferty rule arrangement, and that's very, very useful. And especially fatty acids can be analyzed by converting them into methyl esters, and then you can find out the structure of all the methyl esters which are present in any kind of oil by using the McLafferty rearrangements. Okay, so all of them will give you mass 74. I'm giving you one structure information. This is a pentanoic acid methyl ester. You can see, because it is methyl ester, it has given a base peak at 74. So looking at this peak, without knowing this, I can say that this compound is methyl ester because the base peak is at 74. Okay, so that is so easily one can cover this. Okay, so this is another thing. When you have alkyl benzenes, you get a tropylium ion at mass 91. Okay, so, and alkyl benzenes are very, very common kind of compounds which are used in surfactants, and they always give you tropylium ion at 91 mass, and that will convert an alkyl benzene. Okay, so these are some of the neutral loss and
Excuse me,
their
sir.
probable groups which are there. So when there is a neutral loss in it, it could be a methyl group. So like that, all these tables which there, group is lost from the molecule. So these are all the neutral loss and probable groups, and these are the possible formula for the compound. So when you get ion of this mass in the mass spectra, it could be because of this. When you see a mass at 43, it could be because of this. Okay, so C3H7 has same mass. Okay, so like that, uh, COCH3 is 43. Okay, so you get the information about the ion very clearly by looking at the ion. Tables help you to find out information. Okay, well, so so EI
Excuse me, sir.
spectra is very useful in finding out the structure because you have a library. So there is more than, as I said, 3 lakhs of compounds and their spectra are stored in the library. So you can easily find out no library. Okay, so for LCMS, you have to look at the elucidation of structure by collision-induced dissociation by this vector, known and unknown. Okay, so you can divide the compounds in that basis. Class 1, confirmation of presence, because this is a known compound and you are getting expected spectra, so you can easily confirm that. Class 2, matching obtained data with knowledge base. Okay, so many a times when we work on impurities of a compound, we know the original compound and we are looking the expected impurity from that compound. So it could have similar structure. So from that, we can find out the impurity because we know something about it. Okay. Then class 3 is totally unknown. So known compounds can be easily identified even if I do not have a library. But unknown, you require a related to parent compound in the sample. So parent is the original molecule. If the compound is related to parent, you can easily identify that. But it is totally new. De novo means totally new compound. I have no idea about that compound. Then identification of structure is difficult. You will have to make use of several other techniques like NMR, IR, etc. And even the elemental composition, even the molecular, the melting point or boiling point of the compound, such kind of information, whatever additional information you can get, you can find out the structure of the compound. Okay. So there are a lot of knowledge base available. So there are software tools available. One can use, some of them are easily available free of charge. Some of them are paid. So you can have the software tool available on your computer, and then you can use the software tool. I think that's all about. I had to really rush through all my presentation, but then the LCMS and GCMS are used for many of such applications. I will quickly run through few slides. Pharmacokinetics, formulation, QC and production, contract research organization, generic drug companies use it, pharmaceutical industry use them very much. They are used in biotechnology, protein characterization, proteomics application, because nowadays we are having a biopharmaceutical where the impurities and the main drug could be on the basis of proteins. So you can identify them by using mass spectrometry. Nucleotides, carbohydrates, hyphenated techniques in the agrochemical, again, compound discovery, metabolism, toxicology studies, pharmacokinetic studies, QC and production of agricultural products. Italics, they want to find out structure. Detergents, especially those people use enzymes in detergent for better performance. They have enzymes in detergents, polymers, especially a lot of people do reverse engineering, and they want to identify the compounds which are used by others in their polymers. Quantification, pesticides and antibiotics in water. Food, again, chemical contaminants, toxic compounds in food, antibiotics and again contaminants and illegal substances. Scene of crime, so forensic science, people use it in many areas. Horse race doping, explosives, all the explosives can be very easily identified by GCMS or LCMS. Drugs of abuse, banknotes can be studied for any kind of malfunction in any of these areas. Neonatal which is generally used, the level of drugs in the patients. Drugs of abuse, again, hyphenated techniques in academia related to all the above, especially research. So all these as it is. Okay. Okay. Again, I don't know why it is coming again. Yeah. Yeah. Okay. Okay. Fine. Yeah. This is a new field which is coming. RD is made, and you have the area which is affected by cancerous proteins. So that kind of a work can be done by using MARDI as a technique. These are projection, immunoaffinity separations for drug complex separation of proteins and peptides. It is going to be used very effectively. Structural elucidation of active ingredients, metabolites, assays for biochemical indicators of disease stage, dope testing, forensic science, which is always upcoming because there are cheaters, and those cheaters need to be found out, and for that it is used. New diseases, new biomarkers, development of new, because of that the industries continuously face new challenges. Because of that, new technologies and new instruments are getting developed. Some of the things I wanted to show, but because of the time, I could not show you whatever the new developments which are happening. Okay. Well, I stop here. I think I've taken a little more time than allotted to me. If I'm, yeah, any questions from anybody?
Thank
Sorry
you so
for
much,
the rush.
sir. Thank you so much, sir, for a wonderful session.
Yeah,
There are a few
please.
questions that have come on the chat boxes from our audiences, and I would like to address them to you. So the first question is,
Yeah, please.
um, so what is the role of the relative abundance in mass spectroscopy?
Sorry. Can you bit little loudly?
What is the role of the
Yeah.
relative
What is
abundance
the
in
role?
relative abundance? What is the role of relative abundance in mass spectroscopy?
Yeah. Yeah. Okay. Now, the relative abundance is the spectra which you get irrespective of the concentration of the molecule which you have taken. Okay, whatever compound you have, even if it is 5 ppm, 10 ppm, or 100 ppm, the intensity of the peaks will change because the concentration is different. But when you consider relative abundance, the spectra would look exactly identical whether it is 5 ppm or 10 ppm or 100 ppm. So irrespective of concentration, I get exactly same spectra for every molecule. Okay, I am not bothered about its concentration. So when I look at relative abundance, I get the spectra which is common. And other thing is the ratio calculation becomes easy because the base peak is considered to be 100. And with respect to that, other peaks are measured in percentage. So those ratios become very easy to calculate. And from that, one can easily identify the structure because not only the m by z value, the mass which is important, but the ratios of all those masses with each other are also important in finding out the structure of a molecule. And that is why this relative abundance spectra is more important than the actual spectra. So the actual spectra is converted into relative abundance spectra considering base peak as 100. Okay, I can give simple example. If somebody gets the out of 60, 62 marks, I mean 58 marks out of 60, 58 marks, and somebody get out of 180 marks. Now how you compare them? Now unless and until both the marks are converted into 100%, you will not be able to compare them. So it is same thing. So we have to have something which is a relative scale. So that is why we use relative abundance.
Okay, I will be taking just
Clear?
one question. So, yeah, continue, sir.
Yeah. Any other question?
Yes, sir. There are more questions. So the
Like,
next question is that mass spectroscopy has been known for the characterization of inorganic nanoparticles. Can it be done for organic nanoparticles as well?
one minute.
Sure, sir.
Your voice is breaking for me. I'm not very clearly getting it.
I
Can
will
you
just,
repeat the question
yeah,
again?
I will repeat the question. We have known that mass spectroscopy has been used for
Yeah,
the
please.
analysis of inorganic nanoparticles. Could it be used for organic nanoparticles as well?
Mhm. Yeah, it can be used for nanoparticles as well as inorganic nanoparticles. Only the thing is that you have to ionize the compound. Okay, so you have to have it in solution and ionize it, and then you can use it. Okay, so unless and until it is in a vapor phase, mass analyzer will not be able to do that. So as a nanoparticle, you may not be able to do anything, but what is the structure of that nanoparticle? You will be able to get it by dissolving it, converting into vapor, and then analyzing it. Okay, for inorganic nanoparticles, we use PMS to find out what is nanoparticles. Okay, so if you make silver or gold nanoparticles, what are other things present with that? You can find out by using ICP-MS. And if it is organic nanoparticles, You have to find out the structure of that. You have to again dissolve it and use any of the tool like electrospray ionization and ionize it and measure the mass spectra of that. So it is done in that way, not directly. As ACM and TM can take direct nanoparticles and measure it, it is not possible here to directly measure a nanoparticle.
Okay, thank you so much, sir. Sir, but there are
Yeah,
many more questions that are there, but due to time constraints, could I ask the participants to
yeah,
email you their questions, sir?
yeah. And on my presentation, the first slide, my email ID was there. Okay, so I can put it again and quickly, if somebody wants to have a look at it, can write to me. Okay, so
Thank you so
this
much.
is my email ID. Yeah, so they can note it down and they can write to me. Okay, on my email ID.
Thank you so much, sir. I would now like
Thank
request.
you so much, and I would like to thank the Xavier's College for giving me this opportunity and having this nice idea about know your molecule as a subject or a theme for this particular seminar or workshop. And I'm very thankful to all the participants as well as the staff members of St. Xavier's College. Thank you so much.
I would now request Himanshu, sir, from our department to come and address the gathering and to express our gratitude to Dr. Ajit Datar. Over to you,
Thank
Himanshu.
you.
Afternoon, all. Am I audible?
Yes, yes.
Okay. So, on behalf of the Department of Chemistry, St. Xavier's College, and our dear audience, I take this opportunity to thank Dr. Ajit Datar for his enlightening knowledge that he shared today. Thank you, sir, for giving deep insights into the topic of GCMS and LCMS, and also for revealing some interesting facts. I also thank you, sir, for your valuable time and solving the doubts of our participants. I'm pretty sure that the precious knowledge that you gave today will definitely help us in our studies and future. Thank you, sir, once again.
My pleasure, and thank you so much to you also.
I would now request Dr. Nikhila Bhatt to address the entire conference. And on the end of the participants, you could express your gratitude to the speakers and our sirs on the Zoom chat. Thank you so much. Over to you, Dr. Nikhila.
Thank you, Kyle. Good afternoon, everyone. It is rightly said that no duty is more urgent than that of returning the thanks. Today, I take this opportunity to put all my gratitude into words. Respected speakers, our most valued invited guests, and all the participants. It is my privilege to have been asked to propose a vote of thanks for this online workshop. On behalf of the Department of Chemistry, St. Xavier's College, Mumbai, I, Dr. Nikhila Bhatt, Assistant Professor in Chemistry, along with the entire organizing committee, extend a very hearty vote of thanks to all our distinguished speakers. Dr. Anurag Gaur, Dr. Premchand Jain, Dr. Sujata Kashyap, and Dr. Ajit Datar, sir, for their excellent presentations and for making this workshop very meaningful and interesting. I express my sincere gratitude to the chief guest of our workshop, Dr. Ravindra Deshmukh sir, who took his valuable time off from his busy schedule and graced us with his presence and guidance. I would also like to thank Dr. Rajendra Shinde sir, Principal, St. Xavier's Autonomous College, Mumbai, Professor Marzban Kotwal sir, our beloved head of the department, and Dr. Geeta Kotian ma'am, the Vice Chairperson for the workshop, for their immense cooperation and encouragement in the smooth organization of this event. We are also grateful to RUSA, Rashtriya Uchchatar Shiksha Abhiyan, for sponsoring this event. On this note, I must mention a deep sense of appreciation to Dr. Abhilasha Jain, the convener of the event, for making this workshop a grand success. Well, we all know that an event like this cannot happen overnight. The wheels started rolling weeks ago as it required meticulous planning and immense efforts to put things in place. We have been fortunate enough to be backed by a team of very motivated and dedicated colleagues of our department who know their job well and are result oriented. A special thanks to the organizing committee and to all our staff who have directly or indirectly contributed to the successful execution of the workshop. Finally, I would like to take this opportunity to place on record our heartfelt thanks to Mr. Kyle Mayers for all the technical assistance and Ms. Neha Kapadia for all the creative assistance. Last but not the least, I would sincerely like to thank all the diligent participants for your cordial cooperation and patient listening throughout the workshop. Your wholehearted participation made this workshop very interactive. Thank you, one and all. Please note that a feedback form link will be put up on the Zoom chat box and also on the YouTube chat box only. Please fill the same correctly. E-certificates will only be issued to the registered participants who have filled the feedback form. Please do not leave the WhatsApp group until you receive your certificates. And kindly note that you will receive your e-certificates only on your registered email IDs and it may require 7 to 10 days. Please remain patient. Have a great day ahead. Take care. Thank you once again.
Thank you, Nikhila. Kyle, I need to ask you to run the poll for this session as well.
Yes, I was just going to do that only.
Okay. And participants are requested to answer the poll question as well as fill the feedback form which is given in the chat box.